we go. Okay, Chemistry 3111. So now we are on to Chapter 16, which deals with conjugated pi systems and pericyclic reactions. Some of the major points that you're going to take home from this chapter would be what a conjugated system is. And when we say that something is conjugated, all we mean is that double bonds and single bonds alternate. So you have a single bond and then a double bond, and then a single bond, and then a double bond. Okay, that's all it means by conjugated. So if you're wondering, hey, wouldn't benzene be a conjugated system, right? Because it goes double, single, double, single, double, you'd be absolutely right. So that's all conjugated systems means. And then for pericyclic reactions, there are a bunch of pericyclic reactions covered in this chapter, but the main one that you need to know is called the Diels-Alder reaction, because they won a Nobel Prize for it, and it is a very cool reaction. As far as sections that you don't need to worry about in this chapter, I'm going to write them up here for you. So we are going to skip from the fourth edition. We're going to skip 16.8 all the way to 16.13. Okay, you don't have to worry about those. So that's a huge chunk, 16.8 to 16.13. And then I would also add 16.3. I'll say that's more of an FYI. If you want to read it, you don't need to cover it in order to cover the rest of the content that we go over in this chapter. So with that in mind, let's start it by talking about dienes, right? You're probably like, I am diene. I'm taking organic chemistry. It's like, why, Lord, why? Anyhow, so a diene, as you can imagine, is just two alkenes, right, in the same compound. And so there's three types of dienes you can have. There's one where you have two double bonds on the same carbon. That's called cumulated. So there's a carbon here where that dot is. That dot is just a convention that we use to show everybody that this is not some just super long double bond. I'm kidding. But anyhow, so this means this little dot here, this black dot that I shaded in blue, that means there's a carbon in here. So of course there's a carbon here with two hydrogens, and then there's a carbon here with one hydrogen, and then of course this methyl group. So that's what we call a cumulated double bond. The conjugated, like I told you on the first slide, it's when you have double, single alternating. So double, double, single, and then they just alternate over and over. And then isolated is when you have double bonds, but they're separated by more than one single bond. So here we have two single bonds, so those double bonds are isolated. So accumulated, the pi bonds are adjacent. Isolated, the pi bonds are separated by more than one single bond, and the one that we're going to focus on in this chapter is going to be the conjugated ones, which is where the pi bonds are separated by a single bond. They alternate double, single, double, single. So that's what we're concerned with in this class. So if you take a look at the orbital overlap diagrams of the p orbitals for accumulated, conjugated, and isolated system, you can tell there's a huge difference between them, right? In accumulated system, and again, accumulated was when you had this kind of thing here, right? All four of those carbons that I have drawn here, these are all sp2 hybridized. And so in order for there to be two pi bonds on this carbon here, so that's this carbon here, I can fix that, okay? Son of a gun. In order for there to be two pi bonds on there has to be two p orbitals. And so you can see that this p orbital and then this p orbital here, they're perpendicular to each other. And so there isn't orbital overlap the whole way through. In the conjugated system, when it goes double, single, double, like that, everything is sp2 hybridized. There's a p orbital on everything, but you see how they completely overlap. And then when they're isolated, well, obviously they don't overlap in that case. So that's what makes conjugated so special, is that you have a continuously overlapping system of p orbitals. You don't have that when they're accumulated, and you don't have that when they're conjugated. So again, we're going to focus on what? A conjugated system, which doesn't just have to involve carbon. It could be a carbon-carbon double bond and a carbon-oxygen double bond. So you can see that we have a conjugated system right here, right? It goes double, single, double. But this second double bond here involves an oxygen. Same thing below. You could say I've got single. Here, let me get my highlighter out. We have single, double, single, double, single, double, single, double. And you notice that that conjugated system involves a nitrogen. So again, it could involve heteroatoms, like it could involve oxygen or nitrogen, etc. Now you see that this double bond here is not part of the conjugated system. So this double bond, you would say that one is isolated because it certainly isn't cumulated. But again, we are going to focus on conjugated systems. Why? Because you have a continuously overlapping system of p orbitals, and that will be relevant later on. So this first question, all it's asking you is in the following compounds, identify whether the carbon-carbon pi system is cumulated, conjugated, or isolated. So here's cysaconic acid, which you might know from the citric acid cycle. So if I was to go double, single, double, single, double, you can clearly see that this is conjugated, conjugated, whereas this double bond out here, it goes double, single, single before you get to the next double. And so we would say that this one, this one is actually isolated. So isolated. In the next one, it's a similar vein in this cool compound that's found in essential oils, right? We have double, single, double, single. And so that is a conjugated system. So we'll scribble that here. This is conjugated, conjugated. But you see that that other double bond on the far left, you can see that this one is, you got double, and then you've got two singles before you get to the next double. And so this one would be isolated. So here we'll put that one as isolated. Isolated. And then in the last one here, we have the same kind of thing again, where we have double, single, double. Okay, so that is certainly a conjugated system. So we'll scribble that in here, conjugated, conjugated. And then the last one, this one here, is a different color. That one's all by itself. Okay, so that one is also isolated. Probably saying, boy, I hope the next quiz 16 is all that. Now I erased everything, but anyhow, let's see if I can find it. Nope, I lost the chapter and everything. There we go. So I'm sure I lost all of that, but you get the idea. So again, I'll highlight all the conjugated systems. So we'll put conjugated. So this is conjugated. This is conjugated. This is conjugated. And then all of the isolated parts, well, this one, and this one. All right, give me a thumbs up if you're with me on conjugated and isolated. Yes, I can nail that. No problem. Awesome. Let's move on from there and talk about how you would make a conjugated diene, okay? The good news is that all you're going to do is you're going to use, for the preparation, you're going to use some reactions that you learned back in chapter 7, okay? So let's say you had something like this, where you have this bromine here, and then you have a double bond here. Well, you could say, well, all I need is a double bond here, and then it's going to be conjugated. So in that case, you would use a hindered base, like potassium T-butoxide. Why would you use a hindered base? Because an unhindered base would give you some substitution, but you don't want that. All you want is elimination. And so if you use tert-butoxide, it is not a good nucleophile. It's a terrible nucleophile, but it's an excellent base. And so what's it going to do is it's going to abstract a proton, form the double bond, you lose the leaving group, and there you have it. Same thing where you have this vicinal dibromide, the same thing. You would use the base to pull off this proton and this proton. You do two eliminations, and you end up with a conjugated system. So there you go. Now you know how to make a conjugated system using old reactions that we learned way back in chapter 7. Now, a little bit more about double bonds. It says single bonds that are part of a conjugated pi system are actually shorter than typical single bonds. Now, why would that be? Let's think about this. Okay, if you look at a typical single bond between the two carbons in ethane, the bond length is 153 picometers. But if you look at the single bond between these two carbons in 1,3-butadiene, in this case, it's 5 picometers shorter. Well, why would that be? It's got something to do with hybridization, doesn't it, right? These two carbons are sp2 hybridized, whereas the two carbons here are both sp3 hybridized. What do we know about orbital size? As you go from sp3 to sp2, they get smaller. And so if the orbitals become smaller, that means the bonds are going to be shorter, and that's it. So that's all there is to it, okay? You go from a big orbital to a smaller orbital. So of course they have to get closer to overlap, and therefore the bond length is going to be a little bit shorter. So it says here heats of hydrogenation. So if we hydrogenate a double bond, okay, show that conjugated dienes are more stable than if you have two pi bonds that are isolated. Check this out. So this compound here, this is 1-butene, 1-butene. If you take 2 moles of 1-butene and you hydrogenate it, it releases 254 kilojoules of energy for every mole of 1-butene. But again, sorry, for every 2 moles of 1-butene. So you're hydrogenating 2 moles of double bonds. Now, if you take one, this is called 1,3-butadiene. If you hydrogenate 1 mole of it, so it's 2 moles of double bonds, so it's the same number of double bonds, you release less energy. So what does that tell you? It tells you that the conjugated system is lower in energy, and therefore it is more stable. So it's more stabilized because it is conjugated, okay? So as far as the explanation as to why that is, I'm never going to ask you about the rationale behind that, but it is covered a little bit in the textbook. Anyhow, with that in mind, let's see if we can solve a problem that involves stability of a diene. But before we do that, there's one more thing I have to share with you, and that is when we talk about diene stability, the most stable diene that you can have, I'll use a thinner pen here. The most stable diene that you can have is one that is tetrasubstituted. So if we have a double bond like this, and if we have 4 R groups, no hydrogens, okay, that is the most stable, sorry, did I say diene? It's the most stable alkene that we can have. If you have 3 substituents, so let's say you have 2 R groups like this, and then an R group down here, and then a hydrogen, that's going to be less stable than if it's tetrasubstituted. If it's disubstituted, there's 2 possibilities. You can have trans, which is a little more stable than cis because of sterics, but we'll just put them together. So cis and trans, okay? And then the least stable is going to be monosubstituted. I'm kind of running out of space here, but you get my drift, okay? Something like that. So the more substituted our double bond is, the more stable it is. This is actually something that was covered in Organic Chemistry 1, but I imagine you would have, probably forgotten it by now. So with that in mind, if we look at A, B, C, D, let's see if we can figure out which one is going to be the most stable, and then we'll go down to the least stable. All right. So first thing I would do is I would look for a conjugated system. And does anybody have an idea which one of these? There's one that's abundantly clear, hopefully. It's by far the most stable. Anybody? Yeah, it's D, right? Okay, so D is the one that's got the most conjugation. But single, double, single, double, single, double, right? Single, right? So that one is definitely the most stable. So we'll put D at the top here. Is there anyone that looks like the least stable to you? I'd say that one is also maybe not that bad to figure out. Right, it's A. Thanks, Anastasia. It's the one that's got only two double bonds, and they're both isolated. So we'll say here, both isolated. Right, so we'll put A down here. And then it's a battle between B and C, because you notice that in B, you have a conjugated system, and then you've got an isolated part. And then in C, you have an isolated part and a conjugated part. So what I would do is I would look at the substitution in all of these. And if you look at the isolated parts of B and C, okay, you can see that they're both disubstituted, right? This isolated bond is disubstituted, and this isolated bond is disubstituted. So we can't decide off of that. But now if we look at the conjugated system in blue, you can see it's attached to a total of, you've got a carbon here, carbon here, 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 right? So it's attached to, how many different carbons here? 1, 2, 3, 4, 5 different carbons. Whereas if I look at the conjugated system in red, it's attached to 1, 2, 3 carbons overall, right? So the one in B is more substituted, so the one in B should be more stable. And so we're going to say D is the most stable, followed by B, then by C, and then A would be the least stable of all, okay? So just kind of ranking them first based off of conjugation and then substitution. So remember, The more conjugated it is, the more stable it is, and the more substituted it is, the more stable it is. So there you go. Now, what about this molecule, this 1,3-butadiene? So if you remember, I mentioned this compound earlier. So it's basically kind of a study of this compound. So this is called 1,3-butadiene. There we go, 1,3-butadiene. And this bond here is a sigma bond. There's no arguing that that's a sigma bond. And we know that we have rotation around a sigma bond. So it says here that there's two rotational conformations for butadiene. There's S-cis and S-trans. And the S stands for sigma. So when you see the S-cis, this stands for sigma, right? Because it's a sigma bond that is rotating. Now, if you're wondering, why would there be a difference between these two? Well, first of all, it's more sterically hindered when it's cis, right? Because you have these two CH2 groups that are closer to each other. But also, you need to know that there's a barrier of rotation between these two. Why? Because if you look at both of these, you have a continuously overlapping system of p orbitals when it's cis, and it's continuously overlapping when it's trans. But when you rotate the sigma bond, you have to break the orbital overlap here. And you can see that shown, not here, you see it shown right here. So when you get to the top here, you have to break the overlap. Okay, so it's going to be 15 kilojoules less stable than the S-cis, or the S-trans. And again, you have to break that orbital overlap. So you see it here. The S-cis is less stable than the S-trans based off of sterics. However, there is a barrier of rotation because you have to break the orbital overlap here when you rotate that sigma bond. Anyhow, I'll erase that. It's kind of ugly. All right, there we go. So the section on molecular orbital theory, I'm not going to go over this in detail. I'm going to leave this as an FYI because you don't need the MO theory to cover up to section 16.7. We don't do beyond 16.8, where you do need the MO theory to solve some of the problems. But as a chemistry student at the 3000 level, you should know that molecular orbitals are made from combinations of atomic orbitals. The number of atomic orbitals is equal to the number of molecular orbitals. Molecular orbitals can be bonding and anti-bonding. And we're going to use this in chapter 17 to some extent. So you can see that when you overlap two p orbitals to make a pi bond, so this is showing, a p orbital and another p orbital overlapping to make a pi bond like that, you end up with an antibonding orbital and a bonding orbital, and the antibonding is higher in energy than the bonding orbital. And then if you have 1,3-butadiene, okay, like this, now you've got 4 p orbitals, right? You've got one here, one here, one here, one here, one here. So 4 atomic orbitals gives you 4 molecular orbitals, and you start with 0 nodes, 1 node, 2 node, and 3 nodes. And as you increase in the number of nodes, regions where there's no electron density, you increase the energy. Well, how many electrons are there in all the p orbitals? There's 1 electron in each p orbital. So if you follow Hund's rule, the Aufbau principle, you have 1 in the first molecular orbital, the lowest energy, and 1 in this one here. And anything above that is considered to be anti-bonding. And so all of the electrons are in bonding orbitals. Again, even though I'm not going to quiz you on this in detail, it is still an FYI, and you should read the section quickly to make sure you have an understanding, okay? And it kind of goes over it here. So then you can have 1,3,5-hexatriene. So if you have 1, 2, 3, 4, 5, 6, right? You have 1, 3, 5 hexatriene. In that case, you have 6 atomic orbitals to make 6 molecular orbitals. 3 are bonding, 3 are anti-bonding. And yeah, so I'll let you read that on your own time if you want to. So that brings us to section 16.4, which involves electrophilic addition. Okay, so electrophilic addition involves a little bit of Markovnikov chemistry. And we talk about ways that you can add halo acids to a double bond.